Paco Bytes, and I'll be talking about building high-performance autonomous walls on Ethereum. So about me, I work on Concrete. Concrete is an open-source framework for building application-specific rollups. So with Concrete, you get an entire EVM-compatible chain dedicated to your app, which you can enhance so that it better supports your use case. This is a little demo of a game we're working on. What's interesting about this, I'm going to show you very little, it's like 10 seconds. All of this is in Go, so there's no Solidity yet. We use some of the tricks I'm going to tell you about now to make this feel so nice. And of course, if I work on application-specific chains and autonomous walls, something I think about a lot is what the bottlenecks are, what things actually need enhancing, what do we have to make app-specific so that we actually get benefits. So in this talk, there's so many things I want to talk about, but I just only have so much time, so I will focus on state and execution. There's other stuff you can do, like derivation and data availability and so on, which you are already somewhat familiar with. I think the other two are things that are very important, but that you don't hear people discuss so much within the AW community, so that's why I'm focusing on that. So first, I'm going to talk about state and how things get stored in Ethereum. Everything from balances to smart contract storage is going to go into this thing called the Merkle-Patricia tree. And the problem with that is that everything has to be 32 bytes. Everything goes to storage as opposed to having something in memory, like you would in a normal game. And everything is very expensive, and it's even worse because it gets more expensive over time. I'm not going to go deep into that, but just think that if you have a tree and you add data to a tree, the number of internal nodes within the tree is also going to get bigger. And as such, all of the database operations you're going to do in the tree also get slower over time. So just to go through an example, let's say we have some unit that can be dead or alive, and we want to keep track of that. So we have a Boolean, and if we have a normal game server, all of that is going to go in memory, and it's going to take 1 byte, and we can touch that section of memory in 100 nanoseconds. If you do it in Ethereum, one has to go in storage, so it has to be actually in disk. It has to be 32 bytes, and there's thousands of bytes that you have to read from the database, recompute. You recompute the entire Merkle path for the tree, and then you put everything back in storage. So it takes 1,000 times more. So of course, if it's so bad, why do we even do it? The answer is that this is what makes the world autonomous. You need to reach consensus and be able to update the tree very quickly. And you need to be able to reference, validate, and revert to previous states. And you can only do that fast enough with a structure such as the Merkle-Patricia tree. If you were to do this a normal game server, if you put something in memory and then you have to there's some reorg and you have to go back, you have no record of that. There's no state you can reference. So of course that wouldn't work. So what can we do about it? What space do we actually have for making trade-offs so that we can mitigate some of these issues? One is application-specific storage structures. This is something I worked on for a bit. It works, but there's some reasons why it's not so practical. So this is one thing I built where instead of storing everything in the Merkle-Patricia tree, I had this other tree which is called a quad tree, which is very useful for spatial indexing. So if you were to do that in Solidity, you would be effectively storing a tree on top of a tree. So you would have the quad tree, and every node would correspond to a leaf of the Merkle-Patricia tree. So what you can do instead is not put anything in the Merkle-Patricia tree, and instead you come up with this alternative tree, which actually has the same structure as the tree which you are using for indexing. So that's faster, and it uses substantially less disk, and it's also very impractical. There's this thing called snapshotting and prefetching, which modern Ethereum clients do, where I'm not going to go deep into how they work, but basically you want to have another copy of state which is flat as opposed as in a tree, so that you can read it in constant time as opposed to having to go down the tree. And then you have prefetching, which what it does is as the block gets computed, you are going to have this prefetcher go through the tree, at the same time, just so you can have all of the nodes you're going to need later on for recomputing the tree. And all of the, like both of these things are fairly complex, and it took the Geth team like 2 years to be confident on them. And they are also involved with like snap syncing and a bunch of other stuff. So if you want to change the way, like the structure of the tree, you also have to take care of all of these things. So in the end, it's like this big engineering effort that you have to do. While in the end, like the biggest benefit you get is that things take less space on disk, which is great. But unless the things that you're improving are like a substantial fraction or like a big enough fraction of the things you store, it's not actually worth all of the effort you're putting into it. So if you improve like 10% of storage by 70%, that's like 7% improvement, and you have to spend like 2 engineering years on it. Like maybe you can get similar improvements just like working like generic stuff. So yeah, sorry, but you know, bad news. I hope someone like figures things out, or maybe I will. We'll see. So of course, there's something else we can do, which is just like using more resources, but allocating those resources only to this application-specific thing we're doing. So for instance, use more RAM, but we give all of this RAM to only the state that corresponds to one contract, which is the application we're making the chain specific for. And then we actually get advantages. You can think about this as like same way you can increase the node requirements by like 10 times, and you have to use like a very expensive machine to run everything. Well, instead of doing that, you just increase them a little bit, but this little bit you allocate completely to like this application-specific state that you have. And of course, there's like many constraints. The state has to be narrow enough so that you can put all of these in memory, or like most of it, and all such things. But I think it's like more promising in the sense that it's not that hard, and it like gets you some benefits as long as you meet the constraints and you're application specific. Okay, so let's get into execution. Okay, now execution. So again, everything is 32 bytes, no parallelization, memory intensive tasks are very slow, and you have like a bunch of other issues like contract size limit. And again, let's see, let me find my thing. Same thing as storage. There's a reason things are the way they are. So for execution, we need things to be safe, secure, because we are executing arbitrary code. So you don't know what people are going to be doing. You have to be secure in that regard, and everything has to be deterministic so that we can have something to agree on. Because if we had like different execution for different clients, we couldn't agree on things. So what can we do about it? Well, we can use this thing called precompiles. With precompiles, instead of using just like running arbitrary code, you actually like build native code into the client that is way faster. And you can do with things like putting all of the like complex digital physics go into a chain as opposed as on top of the chain like Solidity. I think it's way faster. You can parallelize them, and you could even like hardware accelerate them. Like if you have something that's for some reason like some like cellular automaton that needs like GPU acceleration, you could actually like do that very fast if you like have it a GPU or something. But of course, then you need a GPU for every client. But that might be a trade if you want to make. So how fast are they? They're very fast actually. So for CPU intensive tasks, they're like 25 times faster. For memory intensive, like an order of magnitude more. You can also do this thing where you put a WASM interpreter as a precompile, and then you can just like run arbitrary code in WASM as opposed to the EVM. Working with WASM is actually way harder than you would expect, so there's still like work to be done on that, but I think it's a promising direction. Of course, there's some trade-offs, given that this is not arbitrary code that you deploy, but rather native code that you have to put into a chain, and you have your own chain with this code. Updating things is way harder. If everything goes into a chain, if you want to change the protocol, you have to do a hard fork, which is very inconvenient. Okay, so we've gone through state and execution. Let's think about the future. I think we are going to see some app-specific chains which are enhanced for digital physics, and I plan to build some of those. And I think we are going to see those chains focus on execution, so using precompiles and using them to do things very fast through parallelization, and also derivation, which I didn't talk about, but I think it's something I want to like put in your mind very briefly. So how does that look like? If you think of the kind of classical example of digital physics as the laws of physics, and then like game rules as, let's say, the laws of tennis, the rules of tennis. So when you play tennis, you won't have to like, when you come up with a game of tennis, you won't have to come up with new laws of physics. You have laws of physics built into the universe, and you just like build games on top of that. I think we'll see something similar with this, where all of the things that don't change much but are very performance sensitive, we will see those go into a chain as precompiles, and then we will be able to just like use Solidity and build games on top. So yeah, example, law of gravity and like rules of tennis. The law of gravity doesn't change, but I don't know much about tennis, but I imagine the laws can change. The rules of tennis. Okay, so my post-assembly question. Obviously, I wonder what you think about what should go in-chain and what should go on-chain. You already know my take on this, so I'm not going to comment much more. And I think that's about it. I still have some time left. You can follow me on Twitter. I am probably going to do a playtest for the game you saw a few seconds of if I get it ready enough for this week. So you can text me on Twitter and you can join. And that's it for me for now. Thank you.